with variable dispersion by Vasily Belashov, Kazan Federal University, Russia.
Colleagues, in my keynote speech today I told about some applications of theory of non-dimensional solitons in physics of linear waves in magnetized plasma and waves on shallow water. Now I'd like to discuss some other applications, two other applications. So, after some introductory remarks, I will write basic equations and consider the class of linear generalized KP equation model and its applications in the plasma, including ionospheric application. Thus, my talk is devoted to the problem of dynamics of two-dimensional and three-dimensional solitons and linear waves, describing by the GKP equation in media the varying in time and space dispersion parameters. These nonlinear objects are interesting to that the investigation plays the important role both at study of general wave dynamics and at simulation of nonlinear wave processes in the upper atmosphere, ionosphere, and hydrosphere, and also at study of propagation of wave structures in a magnetized plasma. For example, the cases of variable dispersion take place on studying for the evolution of three-dimensional fast magnetosonic waves in magnetized plasma when dispersion parameters is a function both for magnetic field and electron density, and also of an angle between wave vector and magnetic field. This case realized in the magnetosphere and solar corona. Next example is the two-dimensional linear waves on the surface of shallow water when dispersion parameters is a function of the vector. One more characteristic example is the propagation of certain-like internal gravity waves at heights of the ionosphere F layer in regions with sharp gradients of the ionospheric parameters, including the regions of the fronts of solar terminator and the spot of the solar eclipse. Okay. Now, remember the full set of the dynamical equations written in the generalized form. These are the equation of motion, equation of continuity, the equation of motion for potential, Laplace equation, and boundary conditions in the terminology of waves on the surface of shallow water. These conditions means the condition on water. From this set of equations, keeping in the composition the terms describing nonlinear, dispersive, and dissipative effects with the same accuracy, we have obtained the GKP equation, which is valid when the dispersion law is the following point. For example, for fast magnetosonic waves, the coefficients take the following form, and we can see that the dispersion parameters, beta and gamma, are the functions of time and spatial coefficients. To speak about existence of certain solutions, it's necessary to prove that they can exist in the GKP model. Let's write the GKP equation once again in the 4 is Hamiltonian, which has a sense of energy of the system. And formulate variational problems as variational equation. The sense of this equation is that all finite solutions are the stationary points of Hamiltonian at fixed moment of projection dx. According to Lyapunov's theorem, in dynamical system, the points that correspond to minimum or maximum Hamiltonian are absolutely stable. Considering the informations of Hamiltonian for two-dimensional and three-dimensional space, we have obtained the GPP equation, the Hamiltonian of the GPP equation in the following form with integral coefficients A, B, C, and D. This one. Necessary condition of experiment, sufficient condition of minimum. Solving in common these sets of equations and the inequalities, we have obtained the following results. These pictures show changes of Hamiltonian for two-dimensional and three-dimensional cases for various values for the integral coefficients along these lines. You can see the global minimum of Hamiltonian and local minima of Hamiltonian for two-dimensional and three-dimensional cases. So the stable two-dimensional and three-dimensional systems can be transformed to unstable ones at change of values of dispersion parameters, i.e. the characteristics of medium in the cases of varying dispersion. There are some examples of applications. Second application was discussed in my previous talk, and now let's consider first and third applications. First of them is propagation of the photoelectronic wave beam in magnetized plasma. If these inequalities are valid, we can write the dispersion relation in the following form. And if this inequality is valid, the structure of photoelectronic waves depends on sign of the dispersion coefficients. And near the cone where dispersion changes its sign depends also on sign of dispersion coefficients at fixed derivative. In this case, we can write GPP equation in the following form, where H represents dimensionless the field of the wave. You can see that dispersion coefficients are the functions of time and spatial coordinates. You can see in the left picture three cases for negative dispersion and one case for negative dispersion and two cases A and C for mixed dispersion. And usually regions B and C, in these regions we can observe magnetic sound scattering, and in region A subfocusing, defocusing, and formation of the stationary beam of the photoelectronic waves. But in boundary problem for the three-dimensional stationary ultrasonic wave beam propagated in plasma attended to a field near this cone where dispersion changes its sign. Variations of the dispersion can lead to transformation of a stable wave beam to unstable structure, which will disperses or self-reduces at propagation. Now we'll consider one more example, the internal gravity solitons dynamics in the front regions of the solar terminator and solar eclipse spores. Using the thermal model of the test ionosphere and taking into account these inequalities, we can write dispersion relation in the following form. Here, V is a phase velocity and V phase minimum, minimum phase velocity of small linear waves. Well, taking into account the width linearity for velocity of neutral particles, we obtain the two-dimensional GKP equation without dissipation in the following form. The signs correspond to cases, case of positive and case of negative dispersion. Now, this equation is written in the framework moving with velocity v. Let's consider now the dynamical model of the F layer, describing time dependence of ionospheric characteristics, defining processes of diffusion, ionization, and recombination at heights of F region, i.e. effects of solar terminator influence on the plasma associated with sunrise sunset processes. You can see here ion production and recombination rates, diffusion and scale heights for neutral particles and for ions, temperatures, electron temperature and ion temperature. And P characterizes this gas intermix. This one the time scale, and gamma k, some functions defining effect of influence on corresponding component. Important remark: independence on corresponding scales, T character, and a kind of functions gamma k, the D model will describe a time course of the basic ionospheric parameters for corresponding source. That is equivalent to complement of the problem by initial and boundary conditions. If we choose that character equals 24 hours and corresponding values of basic ionospheric functions and Tm for F layer, then our D model describes the daily variation of the basic ionospheric parameters and can be used to investigate the dynamics of middle and large scale wave structures in the F layer in areas with sharp gradients of ionospheric characteristics in morning and evening sectors, superimposed on a background of small daily changes. For internal gravity waves propagating close to the horizontal plane using this change, we obtain this equation, making in the GKP equation these changes. Let's write the GKP equation in one-dimensional form and using initial condition obtained here, and D model for the solar terminator scales. We solve numerically Cauchy problem for different heights. Z equals 0 is a kind of maximum of electron density in the F layer. Simulation results. Here you can see our simulation results. Left picture shows perturbations in the ionosphere F layer caused by solar terminator in moving sector of ionosphere for winter and for summer. T equals 0 corresponds to the moment of sunrise at height Z equals 0. Our right picture shows the perturbation in the ionosphere layer caused by solar terminator in the evening sector for winter and for summer. Here one can see the soliton light wave forerunners with periods about 40-60 minutes on all pictures. Effect of solar eclipse spot motion. If we choose the character and the values of basic ionospheric function and Tm for a flare corresponding to such source as a solar eclipse spot, that our D model will describe the various effects associated with a passage of the solar eclipse front. Solving the two-dimensional GKP equation, we obtain that the characteristic periods of forerunners of the solar eclipse front are about 3-10 minutes, and its special scales are defined by the parameters of the F layer. This picture shows our simulation result, general view of numerical solution of the GKP equation for function U. This function sends vertical velocity of neutral particles at heights for the F layer for the pulse source of type of solar eclipse spot. You can see the two-dimensional soliton light forerunner of the solar eclipse spot. This one. There are also many other physical applications which can be studied using proposed approaches, but unfortunately we have no time to start them here. Thank you. These pictures show my native city, Kazan, Kazan Kremlin, and Kazan Federal University. This university is known by association with such names as Lev Tolstoy, Vladimir Lenin, Nikolai Lobachevsky. Welcome, Kazan.
Nice. Thank you. Have you any questions?
There is some information. The person was missed. He is here now, and he suggested the following. He will not make his talk, but he will just distribute the text of his talk, which is here, and tomorrow we'll just take 10 minutes to discuss after we read what is written in the text. Is okay?
Пожалуйста.
Yes, yeah.
Дело в том, что я сидел в зале здесь. Недоразумение получилось. Фамилия Черепенник. Я сидел в зале. Значит, сейчас просьба какая? Для того, чтобы не затягивать, у меня доклад распечатан. Я всем отдам. Кому интересно, прочитаю. Кому не нужно будет использовать по назначению. Понятно. Завтра я буду здесь. Да, завтра
Okay, so everything which I told already is now repeated in Russian.
Окей? Окей?
Very long for me as someone who
У меня, да. А на завтра, как послезавтра у нас, я уже понял, не будет. Да. Пожалуйста, передавай. Да? Не будет, да? Вот,
I'm
конечно.
very happy because tomorrow you will be my chairman.
Yes.
Otherwise,
So,
you didn't come. If you didn't come, I had no chairman. So now
завтра вы
I'm
будете
sure that I
председателем на том заседании, на котором
Ну, я, да.
человек делает доклад.
Я вам
он
всем,
вчера,
я вам
да.
задам завтра, скажите, дайте.
А я не собираюсь это делать. Russian.
Маленького
So,
по-русски кто понимает?
Вы
понимаете? Вы понимаете, да? Кто еще понимает? Замечательно. Я очень прошу, русскоязычное население, значит, тут кончится у нас это хозяйство, буквально на несколько минут мы останемся, добро? Ну, небольшой этот самый сабантуйчик с чайком и, значит, так, я, тогда пусть другой выступает, я просто раздам, кто есть. Да, обязательно. Да, еще, поймите, значит, мне перевод, да, я прошу.
Presentation of Professor
Вы
Vasily
скажите,
Yu.
вы скажете, что здесь возможны ошибки, потому что переводила учительница средней школы.
They also
Нет, скажите,
apologize for the possible mistakes in English. Okay?
can discuss this outside. For example,
Нет, нет, нет.
Ну вот он заклад.
Вот он доклад.
Зачем?
Зачем доклад?
Кому интересно прочитать, кому не интересно. А мы соберемся, ну есть тема для разговора.